Hello guys, welcome to our second last session of this dive into deep learning series, in which we will be going to cover part 2 of attention mechanism, which is all about transformers and Bert and GPT-3 and all of those cool pre-trained NLP models that we all know and love essentially. So let's dive into the agenda for today. 30 minutes is going to be about introduction and theory part. And next part is all about coding session, which is of 60 minutes. So outline for that theory is first we will be recapping attention mechanism briefly because I will be going over most of these as we move along. Then we will look into transformer models, and then I will try to explain each and every component. And then we will move on to Bert and GPT-3, GPTs, I should say, and Elmo, right? I guess that's it for the outline. Let's move on to the attention scoring function. Last time, as Pierre mentioned, so this is the attention scoring function. We have keys and queries and values, and then we take the linear combination of it. From that linear combination, we get to know the relationship between keys and queries. That will give us a particular score. That score is going to be really helpful for us to understand the relationship between the two. I will talk more about these relationship as we move along in the context of transformer models. So let's get right into it. And of course, one more thing. Last time we looked into Vadanu's attention. Sorry if I butchered his name. So the basic idea was last time we used the encoder and decoder architecture. We used the RNNs, or I should say GRUs, to and couple that with the attention mechanism in order to achieve a sequence-to-sequence model or encoder decoder essentially, right? But this is not what we are here to talk about. We are here to talk about transformers, which doesn't require us to use uh, any of these models. Like now we don't need to use RNNs, CNNs, or GRUs or LSTM or anything of that sort. We can just rely on attention mechanism as a standalone entity, which turns out to be a really good idea. And this paper, Attention is All You Need, is essentially proving it to be a cornerstone in NLP. And the reason for that is because of really good capacity and really good inductive biases. I guess that's a high level overview. But from technical standpoint, why do we need transformers? Or it turns out that all of the comparisons can be done fully parallel. That wasn't the case with LSTMs because, of course, you are doing that sequentially, right? But you don't have to do that sequentially in the case of transformers. GPUs change the game for the compute part, right? RNN and LSTMs must be computed in serial per token, as I mentioned earlier. So this is the transformer architecture, and this is how it will look like. So I guess this is the most complex architecture we looked at up till now. I will talk about each and every component, what makes it tick essentially as we move along. But this is the higher level architecture. As you can see, it has a lot of components. So let's not waste any more minute and try to decompose it. The first part, first of all, I should mention that it is a encoder and decoder architecture, right? But it is an encoder and decoder architecture that doesn't require us to use RNNs or LSTMs or GRUs, right? It can work on their own. Hence, that is why it's a transformer model in its entirety, right? It is standalone model. So if we look deeper into the left side, first, how are we going to input that? So as we've looked at in the last session, we are using any sentence, right? And then we uh, calculate, or I should say, we looked at its embedding, right? We call that input embeddings in this case. Once we have those input embeddings from those tokens, uh, we can put it into a layer called positional encoding. Let's not call it layer, I guess. We have to add positional encoding into our input embedding. And the reason for that is because as of now, we don't have any sense of sequence, right? So, hi, how are you? Is in its exact same space, right? So we don't know if hi comes first or r comes first, right? For that to uh, help, right? For example, and the reason why do we need a sense of position is because language is sequential, right? So the information, if I scramble this sentence, it is meaningless, essentially, right? So one way to encode position is to just use one hot encoding, right? That is the simplest way you can do that. You can do that. Nobody is stopping you, and it will probably work. But there is a clever technique that the attention is all you need paper came up, is to use sines and cosines. Uh, if we look closer into it, okay, so I will talk more about it in the next slide, but just let me finish this train of thought. So we take our input embeddings and concatenate our positional encoding vector. That will give us a sense of position for each and every input embedding, right? Uh, Now with that gets out of the way, let's look deeper into positional encoding. So the problem, as I mentioned earlier, no recurrence and no convolution. The model has no sense of sequence, right? Which is important for language to work, essentially, right? The solution is to add a vector accounting for position to each input embeddings, right? If I plot these two equations, it will look something like this, right? So here, as you can see, that I have two arguments. One is position and second is ith. So ith is the ith dimension of your position encoding, right? So if I look at the 0th dimension and plot the graph, it will look something like this, right? And if I look at the 50th dimension, for example, it will look something like this. So as you can see, your frequency changes as we change the dimensionality, right? It kind of looks like a Fourier transform. It kind of is in some sense, but let's not go there, essentially. So if I plot this graph and take the value at a particular position, right? What I end up with the values that I can use in order to encode positions, right? Now, if I fix the positions and look at all of the dimensions, it will look something like this. Now, using that information at hand, I can couple these two graphs in its entirety and try to look at the positional encoding as a whole, right? So as you can see, it is 1010101010, right? So it is kind of is like a one hot encoding, but it is very it is you can think of it as a continuous form of one hot encoding, but of course in one hot encoding you are essentially taking one and zeros all along, but in this case you are working with waves and sines and cosines, right? So it will look a lot different, and of course it is continuous. So that is an advantage of using this kind of positional encoding, right? So as you can see, at each and every position, you have different uh, different, I guess, values, right, which will help us to encode positions better than one hot encoding, right? Now, with that gets out of the way, we have the positional encoding vector. We can just concatenate it with our input embeddings, which will give us positional input embeddings, right? Once we have that, we can input that into transformer encoder. So this part is known as transformer encoder. Now, if we look into transformer encoder, what we can see that we can take positional encoding, positional input embeddings, and put it inside multi-head attention, and using this add and norm feed forward and add normalization, I can get encoder input representation. If I look more deeper into multi-headed attention, yeah, yeah, of course. There is also a residual connection, as you can look at this, right? So that your gradient don't get vanished. Um, I guess that's it. That's a higher level overview of an encoder layer. If we look deeper into multi-headed attention, what we find that we have multiple self-attentions, right? So what is a self-attention? So self-attention is nothing but taking your positional input embeddings and copying it into queries and keys, and you have another another vector which is known as values, essentially. So these are just a copy of positional encoding, positional input encoding vectors, right? Nothing fancy here. Then you can take the dot product of queries and keys to get the scores. Why are we doing that? We are doing that because now we know that how each token is related to others, right? So we can have these kind of relationship which turns out to be really helpful for us to understand a particular corpus, right? Once we have that, we can now scale it, uh, uh, and once we scale it, we can add a softmax layer to turn it into probabilities, right? Once we have that, we can take the matrix multiplication of the attention weights, right, with the value, just like what we did in the previous session, I guess, right? This will give us the output. Once we have that, we can concatenate all of those multiple self-attentions, right? So whatever we've done up till now, right, that will give us one self-attention, right? Uh, yes. Yeah, sorry about that. So what we did up till now is for one self-attention, but in multi-headed attention, we do this process nth time, right? In this case, if we have n equals to 2, then we do self-attention 2 times independently, right? And the reason for that is because we get a multiple configuration of the relationship between each and every keys and queries, right? That will give us more capacity to understand our corpus, essentially, right? Uh, Once we have the values from or the outputs from the multi-headed attention, we can move forward and put it inside our next block. But first, of course, in order to refrain from vanishing gradient problem, we can just use a residual connection, right? And then use layer normalization and pointwise feed forward network in order to give them more parameters to work with, essentially, right? Because now we have those multiple linear combinations or multiple non-linear combination, I should say, right? And then we can use in some of those layer normalizations as well as those pointwise feed forward network in order to find the relationship between all of those multiple representations, and which will give us a much better representation, which is kind of a combination of all the previous ones, right? Uh, and of course, in order to refrain from vanishing gradient problem, we can just use the residual connections, right? That's it for the encoder part. I know it's a bit more involved, but a high level overview of a transformer encoder is that you have self attention, which give rise to multi-head self attention, which is just multiple self attentions. Once we have that, and we have also residual connections, uh, and then we have layer normalization, point-wise feed-forward network, and positional encoding, which we've done at the beginning of our transformer encoder, right? So these components encapsulates into transformer encoder layer, essentially, right? You can stack transformer encoder layers, which we will look at the end of it when we will talk about BERT, essentially. But the idea is exactly the same. You can take the output of the encoder model and put it inside another transformer encoder and stack it uh, as much as you like, I guess. Now let's talk about decoder part, right? So as mentioned earlier, you have those output embeddings, right? So yeah, of course, it is shifted right. So the important part in the decoder part is that it has to be auto-regressive, right? So that you can, I guess, predict what will come next from what we have already, essentially. So if you wanted to do IM fine, right? So you can take the IM as right. Uh, and I guess that's it for the output embedding, right? Then we will do positional encoding, just what we mentioned earlier. That will give you the output positional embedding, right? In the decoder multi-headed attention, it will work slightly differently from the encoder part. And the reason for that is because we have something called mask, right? So the idea is that in order to refrain our attention scores from using the information that will come in future, like for example, if I wanted to predict IM, if we already have I and M, we want to predict fine, right? So I want to mask fine uh, from our for our from our attention at a particular location, right? So as you can see, up till now we have start and then we have I and M. So in order for me to not look into that fine score, the score between am and fine, right? So I wanted to block that information. The simplest way of blocking that information is to just mask it. The way we are going to mask it is to just adding point, that's a point-wise addition, by the way. We are adding the scaled scores, right? That scaling is exactly the same. This is divided by 1 upon the dimensionality, right? We are using the scale score and adding it with the look ahead mask, in which we will take the negative infinity of all those values which we wanted to mask, essentially. Why negative infinity, you ask, is because when we take the softmax of it, the negative infinity of softmax is essentially 0. So that will give us the mask, that will mask out those information that we don't want at a particular position. Yeah, exactly, that we don't want at a particular position, right? Once we have those masked scores, right, we can take those multi heads, right? That this entire procedure is for a single head, right? But we can of course use multiple heads, essentially, hence the name multi-headed attention, right? So once we have those outputs, we can push that inside this this block, essentially, right? So what is this? essentially we are taking the queries and keys from the outputs of our encoder, right? And we are taking the values of the of this block from the lower half of our decoder part, essentially. So the values are coming from this side, and the queries and keys are coming from the encoder part. And of course, as you can see, it's just a multi-headed attention, right? Only the inputs are slightly different from one here and one here, essentially, right? And once we have the output, we can take the add and normalize it. Once we have that, we can use residual connection, and as well as we can use feed-forward network. And it's just the same drill, the one that we've looked at earlier in this session, right? I guess after add and norm, we have linear layer and then softmax, which will give us the output probabilities of the word that should come next, essentially, right? So as you can see, it's a linear classifier. It has n class, which is exactly our vocabulary size. We take the softmax of it, and that will give us the prediction of what word will come next. Once we have that, we have our prediction from the decoder part, which is exactly what we want. So I guess that's it. That's it for the encoder and decoder part of the transformer part. As I mentioned earlier, we can stack those encoders and we can stack those decoders in order to increase the capacity as much as we want, right? Of course, it will give us a big toll on our computation power, right? So I guess that's it for the transformers model, although it's a bit more involved, but I guess these small components makes a giant model that turns out to be a really important model in the case of natural language processing, right? So now, because of transformers and because of the rise of transformers, we can look at pre-trained models, right? So until now, the pre-trained models for NLP is not that well understood, and essentially you have to train your model for each and every downstream task, or I should say for each and every architecture, and you can't just do the transfer learning that beautifully as you would now because of these great models, for example, Elmo, GPT, and Bert. So yeah, so basically we use pre-trained models to extract word sentence features for the new task, essentially, right? So the idea is that once we have those models, we can extract features that will best describe a particular sentence, right? This feature which will help us in order to train a particular task in future, right? So classically, it was done using word to vector or other language models, right? But they don't have the contextual understanding of it, right? So often don't update the, of course, we don't often update the pre-trained model models. We need to construct a new model to capture the information needed for new task. Word to vector ignores sequential information. Language models only look in single direction, right? So it is, of course, unidirectional. It can't do bidirectional, essentially, right? But Word can, right? We will look into it as we move on. So glove and word to vector, same word, which this will give you the same pre-trained vector to the same word regardless of the context. But it turns out in language, context is probably one of the most important things to look at when we wanted to have a representation, right? For context sensitive word representation, because of the rise of transformer models, we have things like Elmo GPT, and Bert, where the representation of the words depends on the context, which is exactly what we want. So Elmo encodes context bidirectionally, right? Just like Bert, but uses task-specific architecture, right? So for each task, we have to construct a specific architecture. Although it is trivial to construct architecture in the case of Elmo, right? But you have to uh, have a task-specific architecture nonetheless. GPT is a task agnostic architecture, but encodes context left to right only. It can't do bidirectional. BERT combines the best of both worlds. Essentially, it encodes context bidirectionally and requires minimal architecture changes for a wide range of natural language processing tasks. Now, if we look deeper into BERT, it is a big transformer encoder without decoder. So this is important to understand, right? So we can throw away the decoder part. We can only look at the encoder part. And that will give us the representation necessary for us to tackle the downstream task with as less complexity as possible. Oh yeah, we are, I believe, out of time. So let me quickly move faster, right? I guess. So classically, we have two variants. One is 12 layers large, and one is 24 layer large, right? Trained on large scale corpus. The most important part is this. So it has token embeddings. It has segment embedding. Segment embedding means each different sentence will give you a particular embedding, right? And we have positional embedding as we mentioned earlier, right? The way to train it for the masked language models is to just randomly mask 15% and we will try to predict it. Essentially, for task 2, the sentence prediction, we take 50% of the time, choose the sequential sentence pair, and then the 50% choose the random sequence pairs. Feed the transformer output of is tagged into a tensor layer to predict if it is a sequential pair. So it is uh, it is an unsupervised learning process, right? So you can just give it a corpus and it will try to make sense of this corpus in an unsupervised fashion. Once we have those pre-trained models, right, we can use it in downstream tasks by the means of fine-tuning, right? So BERT returns a feature vector for each tokens that captures the context information. Different fine-tuning tasks use different set of vectors, right? So you can put it inside BERT and that will give you different features, right? And then you can manipulate these features in order to facilitate your downstream tasks. Some of the downstream tasks are sentence prediction, imminent video recognition, question answering, and any more, I guess. So GPT-3 versus BERT, I guess GPT is, as I mentioned earlier, it is not bidirectional, it is unidirectional. It is trained on books corpus, and it is also trained on books corpus, but plus Wikipedia. It is trained for 1 million steps. It is also trained for 1 million steps with a batch size of as following. I guess that's it because we are out of time. I think that's it. If we can look at, you can look inside each and every slide at your own dictionaries. So some fun work. I used the transformer model to generate music. It turns out to be a really good idea, right? I would love to show that, but we are out of time. We will look into it in the discussion board, right? And MLT also have a collection of different GPT-3 tasks and projects that they collected throughout the years, I guess. So I guess that's it from my side. Without further ado, I guess Pierre will guide you through the coding session. So, yeah, I'm looking forward to it.
Yeah, thank you so much, Mrityunjay, for the theory part. Let me share my screen then. Firefox, perfect. So you should be able to see my
Yeah.
Right. Okay. Thanks a lot. Yeah. And just as a quick thing, I would love to see the music transformer. So if we have time during the, I'm not sure how easy it is to bring it up, but if we have time during the Q&A session, um, yeah, we could maybe have a look at it,
Yeah,
depending
it's
on
just
the
a video.
questions we have.
It's a video presentation, I guess.
But yeah, really really cool application actually of the transform model. Okay, so without further ado, good evening, everyone. It's really nice to be here. And tonight we will be coding the transformer step by step. And actually, we will be coding almost all of it, except for the scaled dot product, which computes the attention scores, which we discussed last week. Um, those we will just use already the ones coded from the D2L book. But otherwise, I think I already shared the notebook. If not, if you can, Mrityunjay or Alisher, if you can share the already filled out book with the participants, that would be great. If you joined us already, then you probably already know the drill with the first code of line here. We're just going to import the D2L library because it has a lot of useful methods and functions that we will be reusing, especially for the plotting part, because we don't want to waste any time on that. Oh, actually, sorry, I'm in the wrong. This is the one I want to use, actually. Is it going to work? Okay, cool. So here I successfully installed D2L. And here we have an image again of the transformer model. I think Mrityunjay did a really great job at explaining how it works, but just to give a quick recap again to understand what we're gonna do right now. First, we actually gonna implement each little section here. So the feed forward, add the norm layer, the multi-head attention, as well as the positional encoding. On the left here, you have the encoder part, and on the right side, we have the decoder part. And it actually took a little bit of time for me to um, figure it out until it clicked. But this figure here, what it's actually showing, it's what's called teacher forcing. So we have our inputs from our source language, let's say English, and then we already have the labels for the target language, let's say French, if we are doing uh, machine translation. But the outputs here are shifted right because the first token for the output will be the beginning of sentence token, basically. So that's why the first token for the decoder um, should be a specific token, so the beginning of sentence one. And then it has to predict the next token or the first token of the sentence based on the inputs. So let's get started with the positional encoding. So now we're going to do this part here of the figure, or actually this part here. And maybe something, or I think Mrityunjay already mentioned it, positional encoding is important because we want to give our model the ability to understand the positioning of the tokens in the sequence themselves. Since we are looking at all the tokens at the same time and not sequentially, we have to include this information in one way or another. And this is via this positional encoding. And one thing I've actually never seen learned positional encoding, but apparently it can also be learned. But in our case and in the original transformer paper, this positional encoding was basically fixed according to these functions which Mrityunjay has already shown us. But the idea is really just to have our input plus this positional encoding, and we're just going to add these two tensors together, and we will get our embedding here just before we pass it through the encoder or decoder part of the model. So let's get started here. We're importing basically the libraries as usual. We're gonna also need the math library later. But here I already have the class positional encoding. And all it will actually take as an input is the number of hidden representations. So how big the dimensionality of the hidden representation, whether or not we want to use dropout, and the maximum length of our sequence. And then it's going to be part, or it's going to be a subclass of nn.module. So if you're familiar with PyTorch, you are probably very familiar with this overhead we have here. So here, what we are going to do is to actually create our P matrix. And we're going to initialize this as zeros. And I have here 1 max length and hidden representations. So far, so good. I will also already basically create what's inside this parenthesis here. So I can already pre-compute all the values that I will be having here. So this will be stored in my X matrix, and I will do torch.arange max length the type is gonna be. So here I'm specifying the type because we don't need a really high precision, basically. And we are gonna reshape it here and divide here by torch.power, which will basically generate that part here. Is it, yeah, 10,000. Yeah, I think I'm correct here. And we're gonna do torch.arange 0 non-hidden and again specifying the type here because we want to work with float 32. And finally, just have to check something. This one belongs to this one, that's fine. Here I'm actually gonna divide by the number of hiddens. Okay. And after that, we are gonna add the sine and cosine functions to it. So for the first 2 dimensions, we want to use all. And then we're going to start from the first index. So, and we are going to have a step size of 2. So each second, or from the first, third, fifth column, they all will be passed through the sine function. Whereas for the even numbers, even numbers, they're going to be passed through the cosine function here. Okay. And here I'm gonna define the forward function. So whenever we pass in this input tensor, it's basically gonna take the input tensor and it's gonna add this P matrix to it. X.shape. I'm gonna take the first size here. And we are gonna pass it to the device just in case we are using a GPU. And lastly, we're gonna return this matrix, but we defined the possibility to have a dropout layer here. So just in case you want to use it, we can just add it. And if I run this here, is it okay? It seems to be working. So now I'm just gonna check whether it's really working or not. So here I have encoding dimension and the number of steps I want to use in my sequence, which basically, let's say 32 and 60. I will have my positional encoding, which basically instantiates this class we just defined. Coding dimension 0. I don't want to use dropout here, so I'm just adding 0, but I'm going to put it into evaluation mode. This is again something specific to PyTorch. And then let's create the encoding. Okay, positional encoding. And I'm just going to pass zeros here. Yeah, I need one more. Number of steps I want and my encoding dimension. All right. And finally, I just want to keep some parts of it. So here I'm just going to say here this shape one here. So here I'm just defining my tensor so that we can plot basically the result. Yes, perfect. And what we are plotting here is so in this matrix P, basically each row corresponds to one position in the sequence, and each column corresponds to the one dimension of the hidden representation. And we want to differentiate between them. And you can see that each column here has will have a different frequency, basically. So we will be able to differentiate basically each input token depending on this information. And I will show even a nicer picture where we can see what's happening. But to get a better understanding, the book actually offers a very neat way to visualize it. And it's basically using, I'm going to show you, it's basically showing you how the binary numbers between 0 and 8, and we will see how the frequency is actually changing for each number. So I'm going to explain a little bit better in a second. Just need to get it running. Yes, perfect. So here we have the number in the decimal system, so 0, 1, 2, 3, 4, 5, 6, 7. And here we have the binary representation. And if we look at the most right bit, you will see that the frequency is really high because it's changing basically at every step, right? So it's 0, 1, 0, 1, 0, 1, 0, 1. And for the second bit, the frequency is a bit lower. So it's 0, 0, 1, 1, 0, 0, 1, 1. And for the last one, the frequency is the lowest. So if I know which row it is, basically I can differentiate between all of these numbers. But this information is encoded in these frequencies. So that's the main insight from the positional encoding. And we can actually create a nicer map to show that. So here we have the columns, so the encoding dimension, and here we have the sequence position. And you can see here the first one has the highest frequency. And as we go deeper into the encoding dimension, the lower the frequency gets. So here, from here on, it doesn't even change. But if we considered more dimensions here, we will see that it's going more to the right. So this is the key idea behind the positional encoding. So if we have this matrix and we add it, our model can basically learn to distinguish between the tokens based on their positions. And yeah, I think Mrityunjay already mentioned it during the theory part, but the reason why we're not using this encoding here, but we're using it here, it's for space efficiency because these are continuous values, so it's a bit easier to work with. Okay, so if I go back to the initial figure, we basically covered all of this part. And now we're gonna jump a little bit ahead and we're just gonna go to the feed forward part because it's the easiest one to implement actually. Because as you will see in a second, it's only dense layers. So here we have our first dense layer. And we'll take a number of inputs and it will cast it to the number of hidden representations. We then have an activation function. So in this case, we're going to be using rectified linear units. Oops. Like this. And then we're going to have a second dense layer. Linear. And it's going to go from the hiddens to the number of outputs that we want to have. So these values here are just passed into the during the initialization of that class. So we know what these values will be. And during the forward call, we are just going to return. So the last layer will be the second dense layer. And before that, it has to pass through the activation function. And before that, it has to pass through the first layer. And here we have the input. So we have to, when writing these statements, we have to think a bit backwards, because we are basically going to go from the output back. So here's the second dense layer, the activation, and then the first dense layer here. And if I run it, so far so good, but we actually going to test whether or not it's actually working. So let's say I have 4, 4, and 8. And here I'm going to put my module again in evaluation mode. And then we're just going to pass some, we're just going to pass a tensor full of ones here with batch size, let's say 2, 3, 4 here. And we just want to get the first one. Does it work? Yes, nice. Okay. So it seems that this part here is working as well. So nice. What we've done now is basically this blue part here of the model, which is really just a fully connected module of the encoder layer of the transformer model. But so far, so good, nothing too wild. And now we're going to come to the multi-head attention. And we had a question during the theory part where someone was asking what is actually happening with the outputs of the heads. And basically for the multi-head attention, we get outputs from each head, and then we will concatenate them and pass them through a fully connected layer. And this is the representation which will be passed on to the next layer. So if I come back to my figure here, it will be actually what we're seeing here is this part, this orange part here. And after the fully connected layer, we will be here between the multi-head attention and the add-in norm. Just to say that the heads are concatenated before and pass through a dense layer before being passed on to resolve the issue of the multi-heads. Here, I've already used a lot of code since we don't have too much time. But what I'm going to do is define the parameters and the layers that we need for this multi-head attention. So the first thing we have to do is to define the number of heads we have. And this is being conveniently passed here in the initialization function. Cool. And then we are going to call our attention layer. But here, I'm not going to code it from scratch for the sake of time. I'm just going to use the function which has already been implemented in the library. But if you're really interested, there is some code showing how this method is implemented. It should be in chapter 10. If you want, I can figure out exactly where it is. But if you search for scaled.product attention, you should be able to find this method if you really want to know how this was implemented. But this will basically calculate the attention for us. And before we put the values, keys, and queries into the attention, we actually have to pass them through fully connected layers, as you can see here. So I'm not going to code to this dark blue region here. I'm just going to code to these white parts and the concatenation. So here we have the one for the query will be linear layer. It will take the size of the query array. Yes, thank you. And the number of nodes. Okay, it's probably faster if I just type it out. I thought maybe autocomplete would be faster. But we're gonna do the same thing here for the keys and the values. Doesn't. So here I'm just really defining the linear layers that you can see above here, the big ones. Hidden representation, and then bias, if we want to have some bias as well in our layer. And we also have to code the output layer here, basically. So I'm going to add it here. The words of the output will be in here. Now we're going to go from the hidden representation, of course, to the output size. Actually, sorry, no, we're going to keep. Okay, yeah, we're going to keep it in the hidden representation size, since it's going to be maybe passed to other layers as well. So we don't want to go back necessarily to this output size. Okay, so far so good. We have the forward function here, which will take as input the queries, keys, and values. And here also, because we are using a batch of sentences, we will have to use padding because each sentence has a different length. And we don't want to basically use values which are meaningless because the sentence is shorter. So we need to pass as a parameter, as an argument here, basically how long the valid length is for each sequence. And this will help us to calculate the correct attentions. So once we pass the queries, keys, and values, it calls this self.transpose QKV, which is written here. I'm not going to reimplement it, but what it does, it's just reshaping the tensor in a more convenient way for us. It's just gonna, as you can see here, reshaping and permute the dimensions. It's just to say that here we have the shape of the input, which should be batch size, then the number of queries or key value pairs and non-hiddens. But the output size here will be batch size times the number of heads, and then the number of queries or key value pairs and number of hiddens divided by the number of heads. So this is just gonna reshape the tensor for convenience. Here we will also have to basically duplicate the valid lengths for our computation. But here is where the magic happens. So here we have the output from our self.attention layer, which is this scaled product attention. Maybe it's not these. Maybe it's not scaled actually. I would have to check. But here we are basically calculating the attention based on the queries, keys, and values. And at the end, we will do the, after that, we will do the concatenation. And here we're just gonna reverse the operation of that transpose QKV and pass it through the last fully connected layer here. So what this class multi-head attention is doing is really everything which is shown here. So first taking them, passing them through the fully connected layers, calculating the attention for each head, concatenating all the representations, and then pass it again through a fully connected layer. And we're then actually already done with the multi-head attention. And one of the few things left to do is to code this add and norm, which is the layer normalization and the skip connection that Muten-J has shown us during the theory part. So let's do that. Maybe let me check if I can run this bit. Should be fine. Yeah, okay, cool. Then the add norm. Okay. Here I'm gonna call it dropout function again. And here we're gonna have the layer norm, which is already conveniently coded for us in TensorFlow. And we're gonna use the normalized shape, which is yeah, the normalized. Actually, it's just this value here, so it should be okay. And in the forward function, we are just going to return. So if we think again backwards a bit, it will be sort of the dropout of our initial inputs plus the inputs here. So this is the residual part, and this will be the layer normalization. So this whole module here will be the add norm module of our model. And here we are just going to quickly test the class. And we just need to give it some parameters to work, just to see that it works. Put it again into evaluation mode here, since we have the dropout. So if you don't put this eval, if you don't call this eval method here, basically your dropout is gonna kick in, and we don't really want to see that right now. This is important during training, where we will call add norm.train or just model.train to make sure that dropout and normalization is activated. But during inference, we don't want to have these mechanisms active. So that's why we're calling this function here. And lastly, we're just gonna test on, again, just a tensor of full of ones, whether or not this is working. Actually on 2, since we need to also have the skip part. And if I just return the shape, is it gonna work? Normalized shape is not defined, yes, because this doesn't exist here. So let's try again. All right, sweet, it worked. So we are actually already finished with coding all the parts of the transformer. So congratulations, everyone. All we have to do now is to put all the building blocks together to finally build the transformer model. So let's start with the easier part, which is the encoder. And what we have to do is to first, what we're going to define is called the encoder block. And what it will be, it's just this gray area here. So it includes the multi-head attention, the add and norm layer, as well as the feed forward module. But the transform itself has n times this block. So for now, we're just gonna implement one of these, and later on we will instantiate several blocks and just connect them with each other to have a deeper model. But let's first concentrate on the block here. And what we need to do is first call the multi-head attention that we just coded, and we will be passing key size and query size and value size, because they could be different from each other. as well as the hidden representation, the number of heads that we want, and the dropout, as well, whether or not we want to use bias. But these arguments here are passed during the initialization, so we don't need to take care of them for now. And then we're gonna instantiate the first add norm layer, and this will be our add norm, and we just gonna give it the shape we wanna have, and as well as whether or not to use dropout. Then we have the actually the fully connected part, which is the position wise FFNN here, and we know the number of inputs, the number of hidden, and just the and after that there is a second add norm layer, so we're just going to call it again here, and it's also going to take norm shape as an argument and drop out. Oops, here we go. So I think this is correct, and if we look here at the figure at the top, we just again went we implemented the attention, the add norm, fully connected layer, and then add norm again. So it's sorry, I went a bit too far. It's exactly what we have here. Oh, sorry, what we have here. And now we have to, of course, we have to define the forward layer. And what we're gonna do is, we're gonna split it into two actually. So first we're gonna do it up until the add norm 1. And thinking back again, we are just gonna pass it like this. So first we're calling the self attention on our input, and you can see here I'm passing the input tensor 3 times. This is because the input tensor will be used as the queries, the values, and the keys. So that's why it's self attention. It's really only passing X and then calculating the attention from it. So there is no distinct information. This is really what self-attention is, passing this input tensor 3 times basically. And after calculating the attention, we're gonna do the add norm layer. And then what we're gonna do is return after wait a second, add norm here. I'm gonna pass it, then pass it through the second add norm layer, and then return that. And if I call it here, so far so good. Let's test whether or not my class is working as intended. I'm just gonna create again a tensor with a specific shape. Let's say the valid length. It's actually gonna be different for, so I have a batch size of 2 here, and I'm gonna say that the first valid length is 3 and the second one is 2. And then we're gonna create the encoder block, which is just here what we need. And I'm just gonna use here numbers again, just to make sure that it's basically running. It's a bit tedious because we have to define all of the arguments. I could have actually passed some default arguments here, but this also works, just a bit more tedious. Here, I'm just gonna, and then in my encoder block class or instance, I'm just gonna pass here X and my valid length. And if I check the shape, it will tell me whether or not the code is running. Okay, cool. So here indeed I have batch size 2, a hidden representation, as well as the sequence length. So yeah, pretty nice. It seems to be working as intended. So what we can do now is add multiple of these encoder blocks and create the transformer encoder completely. And to do so, there's a neat trick. I'm not sure if we talked about it in one of the previous sessions, but PyTorch supports defining a part of the model sequentially using this nn.sequential. And what we're going to do is for e in range of the number of layers that we want, we are going to add a block. So in this blocks, we are going to do add module. And then we're going to give the name block to it, plus the position it currently has. So it will be string I. And we're going to pass in the encoder block class here. And again, we have key size, query size, and value size, and the number of hidden representations, the norm shape, the number of inputs for the fully connected layer, of ribbons, and the number of heads. Actually, can I? Is it still okay? Maybe I could just cut it here. Is it? Okay, nice, sweet. Now I'm just gonna add it here. I was saying number of heads, dropout, and finally, whether or not to use bias in our linear layers. And with that, I think we're good to go. And we only have to define the forward function here. And as it's written, I actually copy pasted the code from the D2L book. But since the positional encoding is between -1 and 1, since it's the output from sine and cosine functions, the embedding itself are multiplied by the square root of the embedding dimension to rescale them so that it's numerically a bit easier. So it's just a neat little trick to ease the training. Here we're gonna call the embedding, which should be just embedding layer from PyTorch. And here after the embedding, we're gonna multiply here by the square root of the embedding size as it's saying in the text. So here we're good. We basically added the positional encoding to our initial embeddings, so that's nice. And just to see it later, we're gonna actually also try to catch the attention rate here for each block. So for I and the block of the encoder in enumerate. So this is a neat little function to iterate over each block. What we're going to do is first pass the representation through the block itself. So that's what I'm calling here. And we are also gonna catch and try to store the attention rates. So at the position I, it's gonna be layer. The attention layer, we're gonna take the attention and the attention weights, so that we can plot it later on. And at the end, when we're finished, we are just gonna return X. So if I run this, does it work? Oh. Okay, I have some issue with my naming here. Encoder block object has no attribute attention. Here. Oh, did I make a setting mistake as well? Oh, here. Okay, cool. After correcting these two misspellings, it seems to be working. Very nice. And we're already halfway there, because what we just did is we finished all of that right side here. So this is actually the part which the BERT model is using, so the encoder part. And now, since we're talking about transformers, we will also do the decoder part, which will take as an input for the multi-head attention the output from the encoder part and treat it as a context, so that the model knows what the context is of the source sequence. So if I come back here, decoder, maybe I actually, neat. Yeah, I still have 15 minutes. That's nice. Um, yeah, I think I can take some time and just explain the code. I'm not sure if I have actually something. I still have some bits to write, but for the decoder, we will do something very similar compared to the encoder part. We first define a decoder block, which is exactly this gray area on the right here. So it will consist of a masked multi-head attention layer, add norm layer, a second attention layer, and only after the second attention layer and add norm layer, we pass it through a feed forward layer, basically. So this is exactly what is happening here. If we look at the code, we will pass again very similar arguments than before. We have our first attention, a multi-head attention layer. We have the first add norm layer here. We have the second self-attention layer, as well as the add norm, second add norm layer, and then the fully connected layer. And lastly, oh, there's a third add norm. Yes, okay. So there's even going to be an add norm after the feed forward layer, similar to the encoder. Okay, fair enough. Then we already have defined all of the layers here. And for the forward pass, we are gonna pass in the current um, hidden representation from our decoder, as well as the state, where the state basically is the representation from the encoder. If we look at the picture here, what they call state is basically the output which comes back into here, which will be passed to the multi-head attention. So, yes, it's basically here taking the state. And if we're training, we have to do some reshaping and create this decoder valid length, because it might be different, I think, from the encoder. So this is just to calculate the valid lengths for each sequence. And the first part will be self-attention on the decoder hidden representation of the output sequence. And only then so this is what we see here actually. So X key values, and decoder valid lengths comes from the decoder from the previous layer. But here for the second attention, we use the inputs come from the encoder for the keys and values, but the queries come from the hidden representation from the first add norm here. So that's an important point. And yeah, after that, we pass it through the second add norm, and finally through the fully connected layer, as well as through the add norm. And I'm not sure why, but the state is actually passed back. It's because state, as you can see here, is manipulated, and the key values are added here. But I'm not sure exactly why. I would have to check. But that's why state here is passed back, because it's being transformed in the decoder probably. Okay, but as it may be here, we're just gonna run our code and see if it works. Yeah, I thought it was gonna work since I didn't code anything. So it comes directly from the book. So I would have been surprised if it wasn't gonna run. And we're already at the place where we can code our transformer decoder. So the full decoder. Let me go here. And we're gonna do something very similar as for the encoder, where we are gonna use this sequential object to generate all of our blocks. And then we are gonna iterate again over the number of layers that we want in our decoder. And we're gonna add, oops, we are gonna add modules to it. And here again, we're gonna call it block. Just add the representation I, since I can go from 0 to the number of layers here. And we have to call the decoder block here. And we know we want to have the key size, query size, so the value size, number of hidden representation, the norm shape, the number of inputs for our feed forward, hidden size for our feed forward, and the number of heads that we want in our multi-head attention, as well as the dropout and the block number. And that should be it. And at the end, of course, we are going to have a dense layer, which we will call just dense, because we're not very creative. So here, we're gonna take the hidden representation size and we're gonna project it down to the vocabulary size, because what we want at the end is something which is exactly the size of our vocabulary, such that we can figure out what is the prediction of our model in the end. Here, there is just the init state function to conveniently initialize the encoder outputs and encoder valid lengths. And yeah, I'm just gonna skip over it. And here we just need to define the forward function of the decoder. And it's also here, we first gonna call the positional encoding. And we're gonna use the same trick of multiplying by the square root of the number of hidden size to rescale. It's none.hidden. And then we're gonna call our we're gonna initialize the attention weights. And we're gonna call for each block. And I think our batch size is just gonna be 2. That's why we're gonna initialize it like that. And then well, we go here for block. Here we're gonna enumerate again over each block in our blocks structure. We're gonna call x state. We can't call the block, which with the current representation and the current state. And we are going to store the attention weights here in the first. I want to have I here, which is equal to sorry, no, this 2 here is because we have two attention layers, so we want to store the attention for each of these layers. So that's why we're gonna call here and some misspellings. The book attention, but and we're gonna do the same thing for the other one. Here we go. Okay, here we're just storing the attention rates. But after we've done with that, we are gonna return the output, which is first passed through the dense layer. And we're gonna return the state as well. So here we coded the whole transformer decoder. So we're actually already finished. How are we doing? Yeah, 6 minutes, perfect. So we finished to code all of it. Actually, maybe I have to check the code. There should be a linear layer, so a fully connected layer, and the softmax as well to calculate the output probabilities. But maybe it's not even necessary to have these. But I'm just gonna try to run this. This should be fine. And then this one, okay. Seems to be okay. And then we have, I'm just using the training code from the D2L book. So what we're doing here is to add the number of hidden representations, the number of layers, dropout, batch size, and so on. We're gonna call the device to see if we want to train on GPU or not. And then we define even more parameters that we need to instantiate our encoder and decoder. Here, it's, I think we, maybe not, but this function here, conveniently used from the library, is basically going to create the dataset onto which we want to train. And here we have the encoder part and the decoder part of our model, and we're just going to pass it through this train sec to sec, which I'm also not going to detail. But if we did everything correctly, okay, it's downloading the dataset, which is pretty nice. Is it gonna train? Oh, nice. Okay, cool. Seems to be working. Okay, while it's training here, I think it's a bit slow since I didn't use GPU, but I'm running probably on CPU, so that's why it's going to take a bit of time. But for the evaluation, we are just going to do something simple. We have here English sentences, and we have the French translation, and we are going to calculate the blue score for each of these pairs. And a bit of a spoiler alert, I already trained that model before this session. And as you can see, the model performs, actually it performs perfect on these few sentences, which is kind of interesting because if you look at the scores obtained in the D2L book, I think for one of these sentences, or maybe for two, the score is not perfect. So I don't know why this specific implementation, which is the same as the book, I really didn't do anything crazy, seems to be performing better than the results obtained in the book, which is strange, but maybe they just didn't update the score, or there's some other issue. But since we're almost finished with training here, let me see if it's still keeping the perfect scores. Yeah, okay, you see, still completely perfect score. Nice. But what we can do now is to, for this last sentence, we are going to visualize the attention rates. And if I do that, here I'm just getting the attention rates from it, since we have stored them into this encoder attention rates object. And if I create the heat map, okay, let me actually change the color here of my notebook to something light. Cool, we can read the X and Y labels. Here we have the key positions and we have the query positions. And here will be the calculated attention weights. And you can see that for each head, so this is the first attention layer and this is the second one. You see that the key position and query position and the attentions calculated with it are quite different for each head. Well, arguably for the query positions 5 to 10, I guess, they're probably quite similar. But otherwise, you can see the increase in capacity by adding more heads. And this is more evident when we use the key and queries from the the key and values from the encoder part. So this, as I mentioned earlier, for the first one, the key, query, and value comes from the decoder hidden representation. But for the second one, let me go back here to here, you can see it here again. So the first one, all three come from the previous encoder hidden representation, but for the second one, it comes from the encoder part, which gives it the context. So that's why it's even more pronounced on this second row here. But just to show that the different heads will calculate different attentions for the query key value pairs. And unfortunately, we don't have a lot of time since it's already 8:30. But maybe we can just quickly see the difference between Elmo, GPT, and Bert. I think Mrityunjay very nicely explained the difference, but just as a quick reminder, in Elmo, we have a bidirectional architecture. So it's not just going from left to right in the sequence, but it's going both ways during pre-training, but we have to have a handcrafted architecture for each task that we're interested in. GPT changed that architecture by allowing to pre-train and fine-tune and have the an architecture with very minimal changes. But for the encoder part, it used the unidirectional architecture. So it couldn't use the bidirectionality of the data structure. But BERT basically combines the best of both worlds by allowing a bidirectional architecture by using the transformer encoder, but it also allows us to fine tune on tasks with minimal architecture changes, which is pretty nice. That's why I'm not sure if it's actually still the case, but BERT is a very popular model in NLP. And I'm not sure. I don't think Mrityunjay, maybe you mentioned it. I'm sorry if I missed it, but the input to BERT is a little bit special because we have the positional embeddings and the token embeddings, which we are quite familiar with. But on top of that, we will also have the segment embeddings because as Mrityunjay mentioned, there are two pre-training tasks. The one is the masked language model, but the other one is also, sorry, how was it called? Next sentence prediction. And so for the next sentence prediction, we need to know which tokens belong to which segment, basically. That's why we have to add the segment embedding. But yeah, I think I'm going to stop here since I'm already a bit over time. But just to say that the notebook that we shared today also contains a little bit of code about BERT. And if you're more interested, if I'm not mistaken, I can show it to you in this. Oh, no, that's not what I wanted. Okay. Sorry about that. I cannot.
Yeah, also one thing to mention that in GPT, we don't have encoders, we only have decoders.
Ah, okay. Yeah, thank you. Just want to show you in the book, if you go to chapter 14, natural language processing, pre-training, BERT is explained in 14.8 to 14.10. So if you're more interested in how to pre-train BERT and the data which has been used, yeah, it contains a lot of code which you could follow if you're interested in. But yeah, that's basically it for the coding part.